So now we know that in Newton's second law. Second law, we know that what you said, the rate of change of momentum is directly proportional to the applied unbalanced external force, and the direction of change of momentum is in the direction of applied force. The question is, in the absence of force, which effect we cannot produce? The answer is
So no acceleration.
yeah. Tell me. So if the force is absent to any system, then what it cannot change? Which quantity will not change? Tell me. Siddhant?
Sir, mass of the body.
That is always constant. So if the force is absent, then what will not produce? The second law says what?
So acceleration.
No. If the force is absent, then what will happen?
The body will be in rest.
If force is absent, then momentum will not change.
Momentum.
See, that's the second law. No? Second law is saying that the rate
Yes,
of
sir.
change of momentum is directly proportional to the applied unbalanced external force. So the question is obvious. If I make the force absent, then what will not change?
Momentum.
Momentum will not change. So the absence of force will make sure that momentum is not going to change, right? Absence of force will make sure that momentum of the system will not change. Do you realize this? Yes or no?
Yes, sir.
Yes, sir.
Yes, sir.
See, that you have to follow the definition very strictly. Newton said that the rate of change of momentum is directly proportional to the applied unbalanced external force, and I'm saying the reverse. What I'm saying is, if the force is absent, the cause is not there. Can we have effect without cause? Can we have effect without cause?
No.
No, sir.
You are saying no, but are you guys able to realize this? That the absence of force means the momentum change will never happen. Correct?
Yes, sir.
And if momentum is not changing, it means we can say momentum is going to be constant. Correct?
Yes,
So
sir.
any system which is deprived of force, external force, the momentum of the system will not change. Okay. And that will help you understand the third law. What is third law? Just a moment. Okay. So third law is something which you all know since your childhood. What is third law? Anyone remembers the third law?
Every action has equal and opposite reaction.
For every action here means force, right?
Yes, sir.
For every action there is equal. What is equal? In magnitude. And opposite. What is opposite? In direction. Reaction. Again force. And this is not sufficient. This is half definition. What is the next part of this law? What is the other part of the law? Tell me. Now you don't know. And action and reaction acts on two separate bodies or system. So action, if I am the person who is creating the force, if I'm doing the action, then the reaction will come from other body. So my action will act on the other body and the reaction will come to me. If I am the person who is creating the action, so I will be receiving the reaction from the other body. So my action goes to other body and the reaction I'm receiving. So action reaction cannot be part of the same body. So there's always two bodies involved. So action reaction always comes in a pair. Okay. So action reaction comes as a pair. So what is the best example of action reaction? So do you all walk?
Yes, sir.
Hello. So have you realized that how you walk ever? Try to decode you walking.
Yes, sir.
So how you walk? What you do exactly to walk? Just walk one step and tell me what you did. Everyone, walk one step, come back to me, tell me what you did to walk one step. Do it very slowly so that you can understand what is happening there. So how you walk? Any idea? Any idea how you walk?
Yes, sir. Your foot applies a force against the ground, and the ground gives you an opposite reaction.
So what you do? You push the ground or you pull the ground?
Push the ground.
With your bare foot, right? So with your sole of the shoe or slipper or foot, you push the ground backward.
Yes.
So ground receives the force in the backward direction, correct? Isn't it? I'll come to that, what exactly ground does, but what you generally do is you try to create a backward component force. So you push the ground backward. Do you go backward or do you go forward?
Forward.
How you move?
Forward.
So the question is, who moves forward? Like who moves you? Your action or the reaction?
The reaction.
How many of you are able to realize this? That you push the ground backward, which in turn gives you force forward, and that force enables you to move forward. Once again, to walk, you push the ground backward. In return, you get the force forward because of the ground. That's third law. And that enables you to walk. So do you walk because of yourself or because of the force which enables you? So you are moving forward because of the force by the ground, or you can also actually walk without that force. Is it possible?
No, sir.
So imagine if you try to walk on ice. So it is said that it's very difficult to walk on ice because it's slippery. So there is no, you can say, action which you can create on the ice. So since you fail to create the action, you don't get any reaction. So if you try to move your foot backward, what will happen? Your foot will go. If you try to push the ice backward, what will happen? What do you expect? How your foot will move?
Yes, sir.
It will only go backward, isn't it? It will go backward itself, correct? So
Yes.
there's some force called friction that we'll study later on. So that friction is a force which holds your foot. and because it holds your foot, so your left foot, let's say your left foot is, held at rest by the ground using some force which you don't see, the friction. And then you're able to lift the front foot and move in air and then again put it back on the surface. Walking is a complex phenomenon. So you hold your foot, you don't hold, you try to push the ground is holding you back. It is not letting you go back. It is preventing the backward motion of your foot. By applying a forward force, you lift the other leg in air, you move across and put it back. Correct? And then when you do the next step, that front foot becomes the back foot, does the same thing, and let you again move in air, put your foot on the front, and this is how you walk. So later on, you will realize that the walking is a falling process. You actually fall, but when you fall, you balance yourself. You have learned this art of walking with a rigorous practice of roughly 1 year. So as a child, you know that it takes 1.5 years to walk, right? They are not able to walk after birth, isn't it? Because of many reasons. The one reason is, of course, the muscle strength is not enough. So they can walk, they can crawl actually. But after 1 year, they get the sufficient strength and a training also by their parents or grandparents. And what they do? They hold the hand and they let them walk. So if you have seen, a child will lift the leg, the foot, and not able to put it properly, isn't it? They fall actually when they try on their own. Have you seen a child falling while walking?
Yes, sir.
Because they are learning the art of balancing their weight. So the brain is able to, capture all the force, pressure, and all. And it eventually let you learn how to walk. So one fine day you start walking, then one fine day you start running also. Then you start learning bicycling. So there again you fall. Then one fine day you start, understanding how to balance the bicycle. So there is a continuous process of balancing, and the balancing is, it is learned by the brain itself through the surrounding, through the pictures, through practice. And it is a very complex process, to be very honest. It's very complex. It's just like, you train the machine for the year and you give so many coordinates, okay, how to balance yourself when you press your ground asymmetrically by your foot. So even as an elder, we do fall. Sometimes we fail to balance and we do fall. So people of any age, if they are not focused enough, if there is sudden a ditch, and if your foot will fall in that ditch, there is a uneven surface, and there you fail to balance because you haven't learned that art of balancing on an uneven surface if you're not conscious. So every time you go through some new path, it's difficult to walk on such path because you need to again relearn the process. Sometimes you can relearn very quickly. Okay, then people find it's really difficult to you can say difficulty in running also. Sometimes they can walk, but once they start running, they fall. So the body weight is, you need to balance differently. So when you are moving really fast, then you need to know how to balance. And even if you have learned everything, you're mastered in walking, running, let's say you're the Usain Bolt, it's still you find very difficult to walk when the earth is shaking. When there is an earthquake, you can't walk properly. Because we haven't learned how to walk on a vibrating surface. Okay. So that art is still not there. Every time you come across new situation, you fail to walk. So you have learned only one thing, how to walk when things are really normal. Okay. If it is uneven, if it is the earthquake, you fail to walk. But all this while, you have to now look at the world through the lens of force, through the lens of Newton's law. If you do not develop this perspective of looking at every action through the Newton's law, you will find this chapter really difficult. You have to somewhere, kind of unlearn the process of thinking, looking at the things in your way. You may have some, some process of thinking, but you have to relearn the process of thinking through the lens of Newton's laws of motion. Okay. So right now you all are sitting on a chair. Let's say I'm assuming you all are sitting on a chair, right? You all are sitting on a chair.
Yes, sir.
Now, how gravity is pulling you? Down or up?
Downwards.
Are you going downward? Are you really going downward? Yes
No,
or
sir.
no? So have you ever thought that why you're not going downward?
Because the chair is opposite.
So you're in contact with chair and chair is giving you some force in the upward direction. And that force is balancing the gravitational pull. That's why you're not going downward. That's simple. Okay. So the force by the chair on you will have a name later on. You will come to know it's called normal reaction. But the idea is there is a force who is balancing you. You're not balanced by virtue of some miracle. No, it is exactly following the laws of motion. So Newton law, it's easy to read or write, but it is a tedious process to realize. And it will take some time. Before you realize, it will take some time for you to understand the real implication of Newton's laws of motion. It is very easy to say the third law, and 99% students fail to apply it because they have learned to say, they never learn to realize. But now you have to realize saying is not enough. Okay. So you have to answer question as per the logic, not as per your own emotion. Because generally what happens, the real hindrance in learning this chapter is your emotional idea, which you have been carrying, something like a intuition. So you do have some intuition which you have developed over the years, but those intuitions are not scientific. So you have to relearn everything and think in terms of, in context of laws of motion. Okay. And if two forces acting on you are balanced, then will you accelerate? The answer is no. So to accelerate a body, what we need? We need a net force, isn't it?
Yes, sir.
And net force will only come when one of the forces is not equal to other, right? So if two forces are acting on the opposite direction, if there is a block and you apply some force F1 here, if you apply some force F2 here, if F1, F2 are not equal, then what will happen? It will accelerate either right or left. Yes or no? So you're applying two force. Okay, when you apply force, do you see motion? Do you see motion the moment you apply force? Do you see the motion? Hello, tell me. You apply force at the moment you apply force, do you see the motion or you see the motion after some time?
After some time.
Because you know why? Because after some time it gains some velocity. So when you observe things as moving, when it is having some velocity, right? So can we say acceleration is motion?
Yes, sir.
No. Acceleration enables motion. Acceleration is not motion. Motion means velocity. So even bodies which are not moving are also accelerating. And bodies which are moving may not be accelerating. Acceleration means ability to change the state. Because acceleration comes from force only. No? So you will come to know later on that acceleration will change the velocity. Which means right now you may not have, but in future, after some time, you will have. So acceleration guarantees that I will change the motion or the state of motion. but acceleration itself is not motion. So a body at rest can have acceleration, but a body at rest cannot have velocity. Do you realize this, what I just said?
Yes, sir.
Anyone? So when you apply force, what you develop? When you apply unbalanced force, what you develop? When you
Velocity.
apply undeveloped, no, when you apply unbalanced force, you develop acceleration. There's a sequence. A net force will develop acceleration, and that will, after some time, will create velocity. If there is no velocity, it will create, and if there is a velocity, it will change. Either it will increase or decrease. Can you think this way? That when
Yes,
we
sir.
apply force, it develops acceleration, but that acceleration will make sure that velocity will change. But that is the future event, not the present event. So force guarantees that it will change the acceleration guarantees that it will change the velocity, because that's the definition of acceleration. It is the rate of change of velocity. How you define acceleration? Rate of change of velocity. So what acceleration guarantees? It will change the velocity. Understood? And see, the way we learned in the past was the effect versus cause. So we are trying to understand the effect, or we were discussing the effect and we are trying to infer the cause. In this chapter, you have to look at the effect with the lens of cause. You have to first figure out what is the cause. Every effect will be, having some precedence, some cause. So the effect is not something which we need to observe now. Now we need to understand what is the cause, and then from that cause, we have to understand what kind of effect it can produce. Are you getting my idea what I'm saying? Tell me, guys, are you getting it what I'm saying?
Yes, sir.
So unbalanced force creates what?
Acceleration.
And acceleration will assure what?
Velocity.
Change of
Change in
velocity.
velocity.
Okay. So if velocity of a body, a particle is changing, can we assert that there must be an acceleration? Can we assert?
Yes, sir.
Yes, we can assert, because see, the velocity is the effect, the cause is the acceleration. Understood? So the way we have learned things in the past, we have to somewhere leave all those method of thinking or learning. We have to develop a new way of thinking, and everything should be very rational. You have to answer things as per the laws of motion, not as per your own emotion. Sometimes we are only emotional. Okay. So let's say if I bang your head on the desk by pressing your head from behind. So what I'm doing? From behind, I'm pressing your head and you bang the desk. This is one event. Okay. Event is clear to all of you?
Yes, sir.
Event is clear now. What I did? I press your head from behind and I banged against the desk. So definitely you will get hurt, but let's try to discuss the physics. If I ask you what I did, the answer was I pushed.
Applying force.
Yeah, I pushed your head, right? Then you banged the desk. So the next force which you receive was from me or from the desk?
From the desk.
So the force acting on your forehead is due to me or due to the desk?
The desk.
Due to the desk.
Due to the desk, because I am applying force behind, not front. So whatever you receive, the front force is due to the desk actually. Now, if I able to think this way, you're very rational. Congratulations. You're into the subject. You cannot be emotional. I am not the one applying force on your forehead. It is the desk applying force on you. Okay. So this is how we have to develop the thinking process. Slowly, steadily, we should be able to think. Okay. So to understand the third law, we'll take some examples. So I hope you have heard about the game called Tug of War. Have you heard this name, Tug of War?
Yes, sir.
So what happens in this game? There are two teams. So there are two teams, right? And both pull the common rope. So there's a common rope, isn't it? So this common rope is, so both the teams are pulling this common rope. Okay. And the rope is taut in the middle. Okay, I have shown it like this, but it should be taut. Just so it's a single piece of rope, right? So let's say there's a two team, team A, team blue, team red. So question is, if a red is the winning team, then which team applies more force on the thread, on the string, on the rope? So to win the game, do we need to apply more force on the, is the more force will be applied by the red team? Or is it more force by the blue team? Let's say this is the winner, the winning team. So can we say that winning team will apply more force on the rope? Can we say like this?
Yes.
Can we say, guys, that the winning team will apply more force?
Yes, sir.
Prasansa, tell me.
Yes, sir.
But the fact is, it is the same rope, and the rope develops a force called tension force. And you will come to know that the tension force in a rope cannot we have two values, it will have only one value. So the winning team or the losing team both apply the same force. And from Newton's third law, if the team A applies force T on the team B, if the blue team applies force T on the team B, then the third law says that the team red will also apply the same force on the team A. Because these are action reaction pair, it cannot be different. So the real question is, what is the role of the rope? So rope is something which gives you the hold. So you all are hanging. It's like you're hanging from the with the help of rope. Then the question is, if the tension is same for both, then how one team wins, another lose? Any guess? Can you guess what will happen? How the winning team is decided? Now, to understand the answer, you have to look at the bottom, the foot. So tell me, the red team is pushing the ground in which direction? Right or left?
Left.
Very good. The red team is pushing the ground left. Very good. So there is a friction force which is acting on the because you're pushing the red team in the forward direction. So the friction force on the team will be the third law. So now the third law is between which? The foot and the ground actually. So the third law says that if you're pushing the ground forward, you will get the force backward. Understood? So the red team is experiencing a net force left. Sorry, a net force right, because you're pushing the ground forward. So the third law says that you will get the force backward. This is the action reaction pair between your foot and the surface. Similarly, the blue team is pushing the ground right. So how the force will act on the blue team? Can we say the blue team will experience force backward?
Yes.
Why? Because you're pushing the ground forward. Now you can see the F and F dash are not same. So to win the match, which one should be more? Let's say all the force on the right is F. If you add net force, and all the left is net is F dash. So what will decide the winning team? Which force? The winning team is decided by the force between the team and the ground. So if the red team is the winner, then which force is greater? F or F dash? Tell me, guys, which one is greater?
Sir, F.
F is greater. See, the winning team having greater. So winning team has actually pushed the ground strongly compared to the losing team. That's the whole idea. So if you try to think of action reaction, here there are three pairs of action reaction. The blue team and the ground, 1. The red team and the ground, 2. And the tension, 3. And because they are holding the same rope, so the tension is going to be same. So tension is not the reason you win. It is the push on the ground which decides the winner. So that is the game of tug of war for you. And I'm sure that before this idea of third law, you all must have been thinking that to win the game, you have to pull the rope tightly, right?
Yes, sir.
But you never realize that actually you need to push the ground strongly. And to push the ground strongly, what they do? They bend as much as possible. Right? If you have seen the game. So to understand all these things in more detail, we'll go later on. I'll show you something more advanced way of thinking. But right now, I'm going to create the third law in mathematical form. We are going to derive the third law from the second law. So derivation of third, or you can say proof of third. So to prove the third law, I'm going to take something called a system which contains two particles. I know this is something which you will not understand much as of now, but this is the beginning of teaching. I mean, when we start teaching the laws of motion, a lot of things we have to teach and we have to repeat again and again as a teacher. So you're listening for the first time. I mean, definitely you'll find it difficult, but after 2-3 revision, eventually you will realize. So this is the first attempt I'm trying to make to teach you this idea. So let's say we have two particles. The first particle having mass m1. And what I'm doing is I'm taking these two particles as a system. Okay. So the idea is there are two types of force. One is called the internal force, another is called the external force, right? So what internal force does? So let's say these are attracting each other. Let's say the M1 is experiencing force due to M2. And there's a way of writing in physics. So this is the two particles. So M1, M2 are two particles. And what I'm doing is I'm not going to apply any external force to the whole system. And if I'm not applying any force to the whole system, then I can say that the M1 will experience force by virtue of 2. So there's a way of writing force on 1 due to 2. This is called the double subscript notation. And similarly, the 2 will experience force due to 1, and we write as F1. What if we have to prove that they are equal in magnitude and opposite in direction? Right now, I have no idea. So we have to go back to the Newton's second law. Okay. And if you look carefully, as per the Newton's second law, the external force will change the momentum of the system. Okay. So let's say the momentum of the first particle is P1 at some instant, and momentum of the particle 2 is P2 at some instant, and it is going to change very soon. Now the question is, who will change the momentum of the M1? For M1, this force is external. For M2, this force is external. But for M1 and M2, the moment you think of M1, M2 as one system, then the force which we describe as external to M1 or M2 suddenly will convert into internal force. Okay. So how we proceed? So second law we apply for. So second applying second law for M1. If you apply second law for M1, what you can write? You have to recall the Newton's second law. As per the Newton's second law, external force equals to rate of change of momentum of the first particle. Can I write like this? Yes or no? Similarly, F21, the force on 2 due to 1. This force will change the momentum of the particle 2. So how many of you are comfortable till here? None of you. No one is comfortable till here?
Yes, sir. Understood.
Understood? Very good.
Yes, sir.
See, this is my attempt. I don't know whether you will be able to understand or not, but I'm at least trying here. Prashant, sir, you got it? What I'm saying?
Yes, sir.
This is second law for you. See, this chapter you have to take very seriously, even more than kinematics. Because once you understand the laws of motion and once you understand kinematics, your job is done. And I can tell you that this is much easier than kinematics. So F12 we can write like this because of second law. F21 I can write like this because of the second law. Okay. What is net momentum of system of two particles, M1 and M2? So can I write the net momentum is the vector sum of each momentum? Yes or no? Can I write? So if I differentiate the net momentum, I can differentiate both sides. Differentiating with respect to time. So dp by dt will be d by dt of p1 plus d by dt of p2. Now the question to you, what will happen to this value? Do we have external force acting on the system? Yes or no?
No.
Which means second law says that if you do not have the external force, you cannot change this. So this must be 0. And we have learned that this we can write as F12 and this we can write as F21. Now, in accordance with the second law, this is what we can write. And therefore, we prove that F12 must be equal to. This is the proof. You can clearly see that the action reaction pair are always equal in magnitude and opposite in direction, and it is taken care by this vector notation. F12 is equal to F2. F12 is equal to F21 with a minus sign, which means they have different opposite direction. And obviously, if F12 is right, F21 will be left. So this is the proof. This is how we prove this third law, and third law can be derived from the second. And second law is a definition, and the first law is actually the laws of motion or law of nature. So in the Newton's third law, when the 3 laws of motion, which we call 3 law, Newton never said these are laws of motion. Newton said that first is the law, second is the empirical relation to express force quantitatively, and the third law is consequence of the second law. Now, I can tell you, it will take some time to digest. It's not easy, I know. So I have full sympathy with you all. If you have not understood, do let me know. I'll try to explain once again. Else, I'll try to go to the next concept. So is this clear?
Yes, sir.
Okay. So let's go to the next concept. What is the next concept? So I gave you some classification of force in the very beginning of this lecture, right? And in the classification, there was a classification under the heading called based on origin. So based on origin, how many types of force we have? Any guess? Rugved, tell me, how many types of force we have?
Based on origin, contact and non-contact.
Excellent. And the contact force we further divided into 2 parts, if you remember. There are 2 types of contact force. Surface contact and
Point contact.
excellent. And under surface contact, we had again 2 force. Normal reaction and friction. And the friction we again have various types. Static friction, kinetic friction, and the third is rolling friction. And under the heading of point contact, we have 2 types of force: tension force and spring force. So this is just a recapitulation of what we have learned already. And now what we're going to do. So these are the actual names. We call the friction force by F. If it is static, we represent by Fs. Kinetic, we represent by Fk. And rolling, Fr. You can just choose a symbolic notation. For normal action, we use capital N. Somewhat stylish, you can keep a normal N, that's totally okay. For tension, the symbol we use is capital T. For spring force, you can write as of now FSP. Just common. These are practices. Okay, we follow these practices. So what I'm going to do is I'm going to show you the exact birth of these forces, how the force came into being. So I'll take a simple example. So this is the example of what? A book on the table. The table is quite smooth, not exactly smooth, quite flat, you can see. And this is your table. All right. So this is the world. This is the your perception in this macro world. This is how the table is. What is the reality? Now, if you try to look beneath that book, if you try to explore the world beneath this, if you try to look from here, macroscopically, you know how it will look like? Macroscopically means at a dimension of nanometer scale. At a dimension of nanometer, even micrometer scale, it will look like this. The surface of the book is something like this. And how the table will look like? Yeah, that's so. So this is the situation. This is the reality. You can see the yellow is the book, and the white is the table. Technically, normally, what we believe that the book is, touching everywhere, right? What is the reality? Is it touching everywhere?
No, sir.
You can see it's touching at very few points, So the actual point of contact is very few. Now, experimentally, it is believed that so experimentally only 1/1,000,000th of the visible area which you believe it is touching makes the actual contact. 1/1,000,000th. Now, even that's it too much, because 1 million means whatever is the area is it touching, the points are really infinite. And these points are actually holding the entire weight of the book. So as a result, what happens? These points, because of the extreme pressure, so under the pressure at the point of actual contact, the two surfaces lock each other and this phenomena is called cold welding. So at the actual point of contact, they get locked together, and this phenomena we call cold welding. Understood? Now, if you try to zoom further, this point, if you try to zoom, you will see there are two surfaces. And within each boundary, there are infinite atoms. These are atoms of the upper surface, and these are atoms of the table surface. And if you take the closest atom further, if you zoom further here, one more step, then you can see the actual atoms. In which you have nucleus, you have the electrons. And you will see a gap between atoms. Are they actually touching? Are they actually touching? You can see. So atoms are not touching. Do you realize this?
Yes, sir.
Two atoms cannot touch each other. If you have studied chemistry a bit, you must be knowing there is something called bond length. So bond length is the minimum separation at which the two molecules, two atoms of a molecule come to rest. And why they come to rest? If you investigate further, you will realize something, that the two positive nuclei repel each other. So there is a repulsion between the positive charges. There is also repulsion of electron versus electron. So we have a repulsion between these two, but we have attraction also. And the attraction is between this plus and this E, or this En. So the electron of one atom and the positive charge of other atom, they attract. And if you investigate further, if you try to go deeper into this entire thing, you need to know something, that the repulsion is a short range effect, which means two atoms generally attract, but only when they come very close, the repulsion begins. What is the idea? Two atoms repel only when they are very, very close. But attraction occurs at a relatively large separation. Okay. Now, when they are very close, there is a repulsion between the atoms. So when they are very close, then the upper atom is repelled by the bunch of lower atoms, and these forces are having a random direction. And there are infinite atoms coming here. See, the scale at which these events are happening is very small scale. It's difficult to realize. At the same time, the atoms of the bottom is also repelled by the above atom. You can see there's a set of repulsion and attraction. And that's why I said in the very beginning that every force in nature is actually electromagnetic force. And mostly you can say electric force. Now we have an interpretation to these forces. Because you can see the forces are having different direction. So we can resolve the force. Okay, we can resolve the force. One we resolve parallel to the surface, another we resolve perpendicular to the surface. So every force, if you take a bunch of force, so you can resolve all the forces. You can resolve all the forces. One parallel to the surface, another perpendicular to the surface. So there are two possibilities. These bunch of forces, if you add all them together, tell me guys, which component can get cancelled? Horizontal or vertical? If we talk about the possibility, which component may get cancelled? Horizontal or vertical? If you think of only red one or only white one, think about it and tell me. If I resolve all the forces horizontally and vertically, then which component will have a chance of getting cancelled?
So vertical.
Vertical can get cancelled. Are you sure? If you think of only red or only white, not both. See, red is what the book will experience and white is what the table will experience. Understood? What is red? The force experienced by the what? Tell me guys, what
By
is
the
red
book.
representing? Force experienced by the
Book.
book. And what is white representing? White arrows?
Force experienced by table.
Force experienced by table. So is it possible that the force experienced by either book or table can have no vertical component? Is it possible? Again, I think you're not realizing it. If I draw a bunch of red line from the origin, I don't know whether they are symmetric or not. Let's say I'm drawing something like this. Now, whether it is symmetric or not, it may have something like this. Tell me which component may cancel each other. These all are forces, the electromagnetic force, 1, 2, 3, 4, 5. So if you resolve into X and Y, then which component may get cancelled?
It's the horizontal component.
How many of you are able to realize this?
Yes, sir.
You can clearly see that the horizontal component we are getting towards right also and towards left also. But the vertical component is only like this, yes or no? So under some symmetry, it is quite possible that these two can get cancelled. Yes or no? But this will never get cancelled, isn't it? Yes or no? Hello,
Yes, sir.
hello. So the component of force perpendicular to the surface in contact, we name this net value as normal. Normal is not one force. Normal is this plus this vertical value. The sum of all vertical force collected from every point of contact is called together normal reaction. So this is your normal reaction. So the question is normal reaction acting at a point or acting over the surface?
Over the surface.
But we represent as a single value. We represent as a single value because that is convenient. So if someone will ask you, is the normal reaction acting at a point or is it is distributed over the surface? What will be your answer? Tell me, what will be your answer? Will you call normal as a point force or distributed force? Tell me. Normal is point force or distributed force? What should be the correct way of saying?
It's a point force.
Come on. Normal is point force. Just we discussed it is acting everywhere.
Yes, it is.
You're collecting the normal from every point of contact, no? There is something called interlocking points. Do you see the interlocking points? I have shown you 3, but how many interlocking points is possible? Infinite.
Yes, sir.
So normal is acting everywhere, yes or no?
Yes, sir.
Normal is a name. There is nothing like a normal. It's of course electromagnetic force. But for our convenience, we are happy to replace the microscopic description by a concrete symbolic description of force. So normal is not a force acting at one point, it is acting everywhere, and the net cumulative value we call normal. And of course, when we are going to draw the free body diagram very soon. There we represent by a single arrow. Just because we represent like this, can we say it's a 1-point force? So what we represent is it is the vertical component of all electromagnetic force. Vertical means component perpendicular to the surface. So if someone will ask you what is normal, what you will answer? Tell me, guys. What is normal reaction?
Distributed force.
And what else? How we represent? It is the aggregate sum of component of electromagnetic force perpendicular to the surface in contact. So how to define normal? So what is normal reaction? Tell me guys, how to define something? See, in physics, we have to understand that definitions are not God gifted. We made definitions so that we can remember, the entire concept in short 1 or 2 lines. So as I always say, definitions are the encapsulation of ideas. So as a learner, if you decode the definition, you can get the idea. And definitions are like encoding of ideas. You encode into something short and brief. You decode to get the whole idea. So how one can define normal reaction? From this entire discussion, if you are the person who is creating a definition for the first time in the life, how are you going to define? How are you going to put into some concrete language? No idea.
So it is a distributed force that acts perpendicular to all surfaces in contact.
So it is the actually sum, it is the aggregate sum of
Electromagnetic force.
force taken in which direction? Taken in the direction normal to the or perpendicular to the surface in contact. Okay. Understood what I just said. Siddhant, tell me.
Yes.
Now, before we answer this question, we also need to ask that why this interlocking developed at first go? Like, what made it interlocking each other? What made it, creating of these forces? You need to go much deeper into this. The book is experiencing some invisible force, and that force is called gravity. So what is the natural tendency of book? To go towards the earth. But what is intercepting? What is stopping it to go from that location to earth? It is the table. So earth is pulling it, but the table is stopping it. And that is why it is pressing the surface. So you can say the one surface is pressed against the other surface. So this pressing is first developed. And as a result of pressing, all this electromagnetic force came to be. And then you took all the component and you said that the component acting normal to the surface is normal reaction. So there is a cause behind this normal. The cause is gravity. So if you start with the sequence of event, the book was first of all pulled by the gravity, which in turn stopped by the table, which in turn developed the electromagnetic force, which in turn created this normal reaction. Do you realize this? Yes or no?
Yes.
So how many of you are able to realize this? Everyone. Yeah, Prashant, tell me, you want to say something?
No, I just raised the hand.
Okay. So the idea is clear to all of you?
Yes, sir.
So what exactly is normal? It's of course, it's a very macroscopic variable, a variable which we have designed to, make all the calculation easier. Okay. So the obvious question is on what factor normal will depend. Imagine if the book and the table both are released from rest under gravity. So I take the table and the book at some height and just release it. So the table will go down with what acceleration?
G.
G. And book will go down with what acceleration?
G.
G. So are they pressing each other?
Yes.
No.
If both are falling with the same acceleration, and if they start from the rest, it means they will have same velocity. So I'm giving you space to go down. I'm not stopping you, isn't it? So table is not stopping the book. Yes or no? Is table stopping the book to go down?
No, sir.
Is it preventing? Is it preventing? Yes or no?
No, sir.
What does it mean? They are not pressing at all. So just because it is visibly in contact doesn't mean it is mathematically in contact. So we also need to get rid of this wrong perception. A normal requires pressing force. A visible diagram in which you see they are touching is not the way to think. Logically, you need to understand that am I stopping the path of the other? And if the answer is yes, then normal will develop because you are kind of stopping it. You're kind of pressing it now. Do you realize this?
Yes, sir.
So to have normal reaction between two surfaces, what is the first requirement? What is the necessary condition? The necessary condition is what?
They should
They
be
should be in
touching each other.
contact.
They must be pressing each other. Understood?
Yes, sir.
So what you realize here? A book on a table is not the only condition to have normal. A book on table under gravity will create the normal. Just because if I drop the same thing. Now imagine I put the same book and the same table inside your apartment elevator. And you press the elevator button, it is start descending down. And let's say it is descending with some acceleration. Now tell me on your regular experience, your accelerator goes down, sorry, your elevator goes down as a free fall or at lesser acceleration? Does it go free fall?
No, sir.
So it must be accelerating less than
G.
G. So a book on a table. Table is descending at what speed? At what acceleration? Less than G? Yes or no? Tell me. Table is descending with a less than G value? Come on, tell me yes or no.
Yes, sir.
Everyone, yes or no?
Yes, sir.
Yes,
See, a
sir.
table and the book is in elevator. You have to see, please reciprocate what I'm saying. A table and the book is in the elevator. Elevator is going down with acceleration less than G. So the table is going down with less than G. So is it allowing the book to free fall or preventing?
Preventing.
Preventing.
Common sense, it's preventing. But the ability of the book is to go as much as G.
Yes, sir.
Okay. So because it is not allowing the book to free fall, it means it is still preventing it, and therefore the book must be pressing the table. Because it is going down with the ability less than its actual ability. And because it is preventing, so it is stopping kind of. So there is a pressing force and therefore there is a normal reaction. Now, if the elevator suddenly, the rope of the elevator breaks and the entire elevator starts free falling, then normal will be there, yes or no? What do you think? Normal is going to be there, yes or no? Hello, hello, hello. Normal between the book and the table will be there. Tell me.
Yes, sir, they will be.
The rope breaks and they are free falling. Normal will be there after that.
No, sir.
Sir, I thought the elevator.
No, I'm saying the elevator is not free falling. The rope of the elevator breaks because of some reason. In that case, the normal reaction will be there, yes or no?
No, sir.
I think none of you are confident. I mean, seems to be all are like somewhere okay, somewhere not understood. Is it very difficult to understand what I'm saying? Yeah, tell me. If it is very difficult, I'll change the way of explaining. So I'll go to the normal things. I will not explain anything deeper as of now. Maybe you will need some time to get mature to learn all this. So is it difficult?
No, sir.
Yeah, be free. I mean, don't hesitate. If it is difficult, let me know. Rugved, are you finding it's very difficult?
No, sir.
Prasansa, are you finding it very difficult?
No, sir.
You all are understanding this? Great.
Yes.
So we'll first write down the. So what is this? Okay, let's say if the horizontal is not canceling each other, if the left is different from the right, you will also have some net horizontal force, right?
Yes.
Not necessarily. But you may have. It could be right, it could be left, it could be zero also. I don't know. But as of now, if I'm assuming there is a net force, this net horizontal force we call friction force. So friction and normal are component coming from the same force. So are they independent or dependent? What do you think? Normal and friction are independent force or dependent force? What do you think?
Sir, independent.
But their birth is from the same thing, no? The root is same. The electromagnetic repulsion. If their birth is from the same cause, how they can be independent?
So because they're exactly perpendicular.
Oh, okay, that's nice.
Just if the horizontal component is also included, then it is independent.
No. Probably what you're saying is in one context correct, but you need to understand that they are component of the same force. It is like you're solving a regular question of vector in which we have a force F and there's the angle theta. So F cos theta or the F sin theta, both are coming from F itself, isn't it? So my question is who is developing these two forces? By the same cause or different cause?
Same cause.
Both are the result of only one cause, no? So in that sense, their origin is independent or origin is dependent? That's the question. Are they from the same origin or different origin?
Same origin.
So similarly, the normal and friction, my question should be normal and friction. Are they from the same origin or different origin?
Same origin.
It is from the same origin. That's why there is a dependent relationship between the two, which will come to know as a laws of friction. I hope this is clear.
Yes, sir.
Yes,
Let's define the normal.
Yes, sir.
Now time has come. Normal reaction. It's a big concept. No. So basically, it is called normal reaction force, but it is so popular that we just say normal. In fact, we don't say reaction or the force word. We simply say normal and we are happy. So we'll start with what is the necessary condition for normal reaction. So what is the necessary condition for normal reaction? The two surfaces must be pressing each other. Am I right? So the two
Yes.
surfaces must be pressing each other. And what is the cause? So it is the aggregate sum of all component of all electromagnetic force taken in the direction perpendicular to surface in contact. Third thing, if you have seen the diagram, tell me normal will push or pull, what it does.
Push.
So it is always of pushing behavior. So normal never pulls, it can only push, nothing else. If you exactly remember these three steps, three things, three concepts, nothing can go wrong. So normal can only push you. It cannot pull. Is this clear? So direction is clear, necessary condition is clear, and the value is clear. Tell me guys, yes or no?
Yes, sir.
Okay, so what is friction? Although friction, of course, I need to teach again, but let's see for the first time here. You are going to forget everything, but again, we'll come back to this chapter, this topic of friction, where you will get the revision. But you should try to understand here as much as possible. So again, the cause of the necessary condition of friction and the necessary condition normal will be same or different?
Same cause.
Cause must be same. It is going to have the same cause. So the necessary condition is what? The two surfaces must be pressing each other. Okay, so that is the same cause. You cannot have the different cause. So I'll write here necessary condition for friction. The two surfaces must be pressing each other, right? And what is this? It is the aggregate sum of component of all electromagnetic force taken in the direction parallel to surface in contact. Now there is a problem. Like what we can say about friction? Is it push force or pull force? Or is it both?
So both.
Very good. Normal is actually friction is actually both. There is no like demarcation. It is only push. It can only pull. Friction can do both. It can pull the surface. It can push the surface. Okay. For example, when you were walking, okay, you're pushing the ground, and the ground was pushing you. But you can do the reverse also. So if you have seen the moonwalk by the Michael Jackson, so in the moonwalk, what he does, he's kind of pulling the surface from front, isn't it? So the push and pull is not well defined. I mean, friction means you can call it push, you can call it push. It is contextual. We cannot say exactly what it is. So you can say it can be of pulling behavior or it can be of pushing behavior as well. It can be of pulling or pushing behavior depending upon condition. So this is the two conditions. So we'll go slightly deeper into friction. And why I'm saying deeper into friction. So I said friction is having again types. So types of friction. And whenever we define something as a type in physics, it means there must be some difference. There must be some rule to classify as either as type 1, type 2, type 3, whatever. So the first thing I said is static friction. So if you look at the same diagram, if you try to pull the book here by applying some force, if the force is very small, probably you can see the book is not moving. It is almost stationary, right? Isn't it? If the force is really small, then book will move or not move. You can check now if you have your laptop on the table. If you press it, push the laptop, is it moving by small force? Or is it stationary?
It's stationary.
Now, if you try to explain this behavior, how you're going to explain the behavior? You're applying some force, so technically the laptop should accelerate, but it is not accelerating. So the question is, who is balancing your force?
Friction.
Because your force is horizontal, so there must be some other horizontal force. But from where you are getting that horizontal force? The answer is, it is a friction. So what happens? In order to move the book, when you apply some force, the motion can only begin when you break these interlocking welding points. It is like a tiny welding, which you don't see. So force, when you apply, this welding point will stretch laterally, sideways. And as a result of the stretch, they develop the attractive force between the pair of atoms on the two sides. So to go deeper again, this is a regular atom, imagine, on the two sides of surface, table and the book side. But when you try to pull the book, as a result, what happens? This atom and this atom will be at some separation, and it is going to be more than before, right? So this increase of separation creates attractive forces, and this attractive force will have a horizontal component, and this component we call static friction. And this lateral moment is very, very small. It's a nanometer scale. So what you need to realize that the force which you apply is balanced by a slightest nanoscale movement of the surface. So we don't see any movement, but the reality is some movement has occurred, but you can't see those movement. Yeah, some movement has occurred. So when you try to push it at a very small scale, there is a movement, but because those movements are not significant, we say it is static. And when friction is studied in this context, when the two surfaces are not moving relatively, the interlocking points are relatively positioned in the same way, same fashion, we call the friction acting in that context as static friction. But it will not hold for longer force. I mean, as you grow the force in value, at some point these interlocking points breaks. But once it breaks, the two surfaces move over each other, and you can see there is a irregularity of the shape, right? You can see the surface is not really smooth, it's irregular. So there is a collision between the two gaps. So again, if I draw some simplified model, so you can just think of zigzag path. So when you move one surface over the other surface, it will go down, will come up, will go down. There is a continuous, collision between the two surfaces. It's like it's stopping, it's hitting here. So these two will hit each other. And there is this is called a soft collision. I mean, of course, these collisions are not something which is very much significant. These are very soft collision. And this collision will slow down the event. And so this kind of collision acts as a sort of opposition to the motion. So what you can realize that the world of kinetic friction having entirely different explanation compared to the world of static friction. Static and the kinetic having different origin. And because of this different origin of the nature, we see friction here only means opposition. Friction doesn't mean always rubbing of two surfaces. Friction means we oppose the motion. Okay, you oppose the relative motion of each other. So when two surfaces are in contact, they oppose the relative motion of each other. So opposition is only for the surface, not for the body. No, this is part you have not understood, but static friction having origin with the cold welding, and kinetic is due to the collision. So here the reason is cold welding / interlocking. But what is the reason for kinetic friction? The reason here is microscopic collision. I'll just mention microscopic collision. And because of the entirely different origin, as the origin is entirely different, it looks both are called friction. Because of some reason, it's just a matter of literature, how we create it. But they have a very different origin, and therefore you need to understand that both are not developed in the same fashion. So in static, what happens? You need to, if you apply some force, they will move slightly and will balance it. If you apply more force, it will move slightly more and again balance it. If you apply even more, it will move slightly more and again balance it. So the beauty of static friction is it is self-adjusting in nature. It can adjust its value as per the requirement. So that's why this is called the. So if I go back to the static friction, I'll just put it here. After this, you can enter this box and read. So for static friction, what you can say? So the point that we should know is it is self-adjusting. So this is like a requirement. You apply force and it will try to balance by moving laterally, shifting a bit. That's it. But kinetic friction is due to, it is not self-adjusting. So it depends on surface irregularity. So if the two surfaces are irregular in a uniform fashion, it means the irregularity, or you can say the curvature, the surface roughness is similar or same throughout the visible area, then kinetic friction is going to be same, assuming the pressing force is also equally distributed. So we say that kinetic friction depends on the surface irregularity. And if you have the two surfaces which are irregular, but the irregularity is uniform throughout, the force of kinetic friction remains same. So they have a different origin. And it is generally constant. So I would say generally constant in value. Generally, not always. Constant in value. And depends on normal reaction. But the static friction is quite different. It's self-adjusting. It is due to the interlocking. So the reason is quite different. Reason one, this reason two, reason 2 and 3. And now the problem with the static friction is that it cannot hold it back forever. Eventually it will break. So there is a range over which it can work. So static friction can go from anywhere to 0, like it is not acting, and it can go to something, the upper limit. And this upper limit, the maximum possible value of, the static friction which we can create between the two surfaces. Again, this is given a different name actually. This is called limiting friction. So of course, limiting is a part of static, but limiting and static are not different. Not same. Static is a concept and limiting is a value it can go to. So it is like if you have 100 rupees in your pocket. So how much you can spend while eating golgappes? Okay. So you can spend nothing if you're not eating at all. What is the maximum you can spend? 100, because that's your capacity. So limiting friction is like what is the possibility of maximum value we can go up to. So that's called the limiting friction. Is this clear? Tell me guys, everyone.
Yes, sir.
So you all have understood? So what is static and what is kinetic and what is like friction in general? I hope this is clear. So friction, what means only when I say what friction, it means opposition. You oppose something. So what you oppose? What we oppose by virtue of this property? Okay, no idea. So what exactly is friction? The definition which you should know or remember now, once you have understood this part. So this is the definition. So what is friction? It is the property of two surfaces in contact due to which it always opposes the relative motion between the point of contacts. I would say point of contacts. And due to which it may support or oppose the motion of a body as well. Now, there is a very common misconception that friction opposes. This is what you have studied, right?
Yes, sir.
But we walk because of friction. We people drive car because of friction. You ride bicycle because of friction. So if you think of bicycle as a whole system, then who is supporting the motion of bicycle in the forward direction? The answer is friction. So when you walk in the forward direction, in any direction, then who is supporting your motion? Again, it's friction.
Friction.
So is friction opposing your motion or
It
supporting your
supports.
motion?
Both.
So friction is supporting your motion as a whole, right? As a human being, you're walking because of friction. People are driving car because of friction. So friction opposes the surfaces in contact, not the body as a whole. So when you try to walk forward, you press the ground backward, friction acts forward. So because your foot is trying to go backward, it is stopping it. So it is opposing the relative tendency of motion of the foot. But that is in a way supporting your motion as a whole. So at some point it is opposing. But when you look at the motion of the body as a whole, it seems like it is supporting. So that's why we say friction opposes the relative motion of points of contact. Okay, points of contact, due to which it may support or oppose the motion of a body as a whole. So that is the friction for you. I hope you got some basic idea of friction. So tell me, guys,
Yes, sir.
how much you have understood today about normal, friction, static, kinetic, both. So there's an obvious question that if two surfaces are extremely smooth, the friction will be 0 or infinite under some pressing force, of course. So highly
0.
smooth surface will create a high friction or low friction or 0 friction. What do you think?
Low or zero
It's a
friction.
0 friction.
And to the contrast to your answer, your or intuition, highly smooth surfaces are extremely rough. I mean, sorry, extremely difficult to move over each other. They have tremendous friction. Now the question is why? Why highly smooth surfaces have very high friction? Ever realized? Okay, now you know this answer. Can you try to explain now what may be the cause? Why highly smooth surfaces are not desirable in many contexts? Okay, let's do some experiment. Do you have your notebooks right now? Any notebook? Any rough notebook which you have used before?
Yes, sir.
And you can
Yes,
see the
sir.
pages are generally very smooth, right? So what you're supposed to do is take just few pages, one page from this book, other from this book. Then like this, just make 3 or 4 layers. That's like this from the two notebooks separate. So just put few pages underneath each other. Done. Just few pages,
Yes,
not all
sir.
pages. 1, 2, or like 3 or 4 pages. That's it. Once you're done, just let me know. Do it with 4 pages at least. Any 4 page will do. And once you're done, just let me know. Make sure it is not the top surface because we need some pressing force. So it should be somewhere between. Is it done?
Yes, sir.
Yes.
Now keep on the desk and try to pull by pulling the sides. So pull this way. Try to pull. Is it easy to pull? Just check.
No, sir.
How difficult it is. It may tear apart the page also. So try to apply more force. See when it is getting pulled. Are you finding this difficult?
Yes, sir.
Tell me, Raghuvat, are you able to pull it?
No, sir.
So these are smooth pages, right? The pages are really smooth. If you check, it's very smooth surface. And it is creating tremendous friction. Can you explain why? Why is smooth surfaces not a good choice to have less friction. So you don't realize something. You know what you don't realize? If you look at this diagram, a rough surface will have less interlocking points. But if the two surfaces are really smooth, highly smooth, then what will happen? The number of interlocking points will become infinite. It means it is not locked at few points, but it is locked at infinite points. And now you have to break all those interlocking points to move. And therefore, the limiting friction will go enormously. In fact, if you make the pages like just 10 pages, or maybe less than that, you cannot pull with any force. It will just tear apart, but you can pull it. So in fact, you can try with two of your friends pulling each other. Of course, you will lose few pages or the book, but you will learn the lesson that it is simply impossible. So highly smooth surface increases the friction enormously. And the answer is why it happens? Any guess? Why it happens? Hello, hello, hello. Why it happens? Tell me.
So because the normal force between the pages are high, that is why the friction
No.
increases.
It is because you make a smooth surface will touch each other at various points. The number of interlocking points will grow.
Yes.
And more the interlocking point, it means you have to break all those points. So you have to overcome the friction of every point. So highly smooth surface creates a large number of interlocking points. Do you realize this? Yes or no?
Yes,
Yes.
sir.
So highly smooth surface creates extreme friction. Have you seen the mobile screen and the scratch guard which comes? The moment you
Yes.
put the scratch guard over the mobile screen, it simply flattens and kind of stick to each other. Whether glue is there or not doesn't matter. Of course, they put extra glue for the extra safety, but even if you have no glue, it stays there. Have you ever realized this? It is airtight. There is not even a single bubble between the scratch guard and the screen. So what kind of surface is the screen and the scratch guard? Can we say this is extremely smooth surface? Can we say?
Yes.
And because it is extremely smooth surface, so they create extreme interlocking connection. And because of this interlocking connection, it is almost impossible to slide the scratch guard parallel to the surface. You can lift it easily, but you cannot slide it. You can try right now also. So is it possible to slide it easily? Can you move the scratch guard sideways by pressing it?
No, sir.
So they have tremendous friction. And the normal reaction is provided by the atmospheric pressure because there is no air beneath the scratch guard and there is only air above it. So that creates atmospheric pressure. And that pressure creates the normal reaction. and hence the friction. So see, you can see here, there are many things which is counterintuitive to your pre-existing ideas, isn't it? So in the beginning, when you're learning this laws of motion or friction, you have to get rid of your your own uh, developed intuition. Rather, you have to learn the concept and recreate those intuition from scratch. So as of now, whatever I'm saying, you have to believe me and you have to listen very, very, very carefully. Every single term which I am saying, you have to listen again and again. Try to kind of imprint in your brain, revise as much as possible. And once you are confident, then go to the next concept. Don't hurry in again finishing this chapter. If you have been in hurry to finish the kinematics, that was the first mistake, and this will be your second mistake. And after third mistake, you will be left with nothing. So you're going to struggle with the entire physics throughout. So if you want to make the journey smoother, listen to every concept very carefully and try to grab it. So such details are not possible to read in book. You're seeing the microscopic world of interaction. Okay, so I hope this is clear. Why smooth surfaces are not favorable? So I can put as a note just for your reference. And what I can write? Extremely smooth surfaces in contact will have a very high friction due to a large number of interlocking points. Which test you have, Shivam?
It's a chemistry test.
But your lecture time is known to you, no?
Yes, sir, but our chemistry sir is taking a test instead of his lecture today.
No, it's still, I mean, you can talk to sir that, okay, keep the lecture, I mean, test from 9 itself. This is our time of,
So it is from 9. Okay, sir.
it is from 9 o'clock. Yeah. So I leave by, 45.
Fine, sir.
See, sometime write the test based on the memory you can recall, not by rote learning. Just before the test, if you are learning something, it means you're not, retaining in your brain. So sometimes test yourself in a different way. Let's see how your brain works when you know nothing, when you have not revised. And I'm, why I'm saying this. Technically, in the actual examination of JEE, you can't revise in half an hour or 1 hour or 1 day also. Because by the time of end of the syllabus will be like a mountain. So you have to always learn, okay, when you learn something at first, go to make it sure that you learn really good. And then try to force yourself to recall the concept which you have learned. That is the right way. Okay, so we have done with the normal and friction. Friction is something which I'm not going to teach right now. Just the idea is sufficient. And the next concept is called tension. We need to understand what is tension. So tension, we have to study in a taut string. So to study the concept of tension, In this chapter, we have to again understand something what. So the first thing. This is called assumption. So the assumption is, or you can say assumptions. String are massless. That's the first assumption. Second, strings are inextensible, which means you cannot stretch it. Okay. And because you cannot stretch it, so the moment you start stretching, without any further deformation, it will stop you by applying a force equivalent of what you apply, or it will develop some tension. So strings are inextensible. You cannot elongate it. So the moment you try to elongate, tension will develop. Okay. So that's the whole idea. Tension will develop when you try to elongate it. Not before that. I mean, if there is no tendency to elongate, it will never create the force. It's just loose rope or a string. So when you try to extend a string, then tension is developed. And that's why the word I have used inextensible. It cannot be extended. So if you try to extend, a tension will develop. If it is extendable, then again it will develop, but the reason will be different. In case of extendable string, when you deform, it also develops a force, but there we don't call tension, we call spring force. So the difference is anything which is inextensible, the tension will come, the word tension comes into picture. And for anything which is extendable, what we call spring. So spring is a concept for deforming objects, and tension is a concept for non-deforming object, or you can say for the object in which deformation is negligible. So this is what you have to assume. First of all, it is massless. Massless means it's a very light in weight, and the overall mass is nothing compared to the mass which we suspend from these strings. Now we need to know something more detailed. So have you heard the name pulley? The pulley is a round object. I hope you all have seen. It will have an axle of rotation. So this is the pulley and this is the axle axis of rotation. And generally we pass a string over the pulley. There is nobody on. This is called the string passing over a pulley. Let's say we have a fixed pulley that many questions will see. Fixed pulley. And you can see a single piece of string is passing over it. Okay. Now the question is what tension does? Tension can pull or push or both. Think about it. Can we push something with the help of a string?
Pull.
It can only pull, right?
Yes.
So a string can only pull. So it is always of pulling behavior. It is always of so what it pulls? It pulls the object connected to it. So if this is the end of string and something is connected to this end, let's say you denote by something, let's say mass or whatever. So these masses, if it is taught, let's say if the string is taught by some other reason, okay, if the string is taught, let's say if I apply a force F here, F dash here. So because the pulley is fixed, you're trying to pull the block in a way, you're trying to extend the string, yes or no? Do you realize that the force is trying to elongate the string?
Yes.
Okay. So whenever you try to extend the string, tension will develop, yes or no?
Yes, sir.
But what is the property of tension? Will it pull or push?
Pull.
So the force on the mass M will act towards left or right? What will the direction of tension? The direction of tension force on the block will be what? The block will experience tension towards left or right?
Right. Left.
So tension can only pull. Na? So how you're going to pull? Let's say you are the rope. How you will pull the mass M? Right or left?
Left.
Left.
So you represent the tension T and you will show by the arrow towards left. Similarly, the tension on the lower block will be in which direction? Right or left?
Left.
Very good. Because tension is always of pulling behavior, so it will be pulled towards left. Understood? But you can realize here that I have shown the tension in both sides of the string T only, not by the different symbol. Do you know why? Do you know why? Okay, you don't. Or you know. Because the strings are massless. And the rule number 1, in a massless string, in one single piece of string, the tension remains same throughout the length. So now this is the first rule which you need to remember. I'll put in a heading. For massless string passing over a smooth pulley. Now pulley is also smooth. So when a massless string passes over a smooth pulley, a pulley without friction is called a smooth pulley. The tension on the two sides remain unchanged. The tension on the two sides remains unchanged. Right now, are you wearing the shirt or t-shirt? Rugved?
Shirt.
Do you have tie?
No.
Anything like a maybe like a rope or string? Anything?
Yes.
Just bring anything, string or rope, anything.
Yes, sir. Got.
Now put over your neck.
Yes.
And try to pull the one end. Is it coming smoothly or is it getting obstructed by the neck?
It is getting obstructed.
Now look at the tension in the side in which you're pulling and the other side. Which one is tighter? The side you're pulling or the other side?
Pulling.
So do you realize that the tension on the two sides are different?
Yes.
That happens when the neck is acting as a pulley and it's a rough pulley. Because it's a rough pulley, it is happening. Now you can take your pencil or pen and put over the other end and try to pull. See what is happening. Is it going without obstruction? Do you feel any obstruction there? Tell me. If you just try to pull over some pen or pencil, whatever,
No, sir.
it's going smoothly.
Yes.
So that is the case when the pulley is smooth. You won't find any difference of tension on the two sides. So the rule is, which you need to remember, a smooth pulley do not change tension whenever a string passes over it. It keeps same. So in this chapter called laws of motion, we are going to deal with smooth pulleys. But after few months, a chapter will come called rotational dynamics. And again, pulley will return back. And when the pulley will come back in that chapter, it will come with mass also, and it will come with friction also. And the moment it will come with mass and friction both, the entire laws of motion will change there, because the rule will not be followed what we are writing or learning here. Because the pulley will be rough, the first thing you have to understand or draw is, if you are drawing the FBD there, the tension will become different. You have to choose T1 and T2 as a symbol on the two sides. And the pulley become massive. And the massive pulley will have a different relation. So we'll come to that. So rule number one is clear. Tell me, guys. First rule is clear.
Yes,
Hello,
sir.
Yes,
hello. Now the tension always acts away from the object considered. It means for block, it will act like this. But if I think of pulley, how tension will act on the pulley? So we look for the point at which you leave the contact. So the part which is touching the pulley, this part is touching the pulley, is not considered. We only consider the part which is not touching the pulley. So this is the boundary of the string, and right of this boundary is the pulley, the string which is not touching the pulley, isn't it? So the part of the string which is in contact with the pulley is called the part of the pulley itself, which means that string we think as a part of the pulley. But this string, the string beyond this point and beyond this point, is the pulley. I mean, is the string which is trying to pull the pulley. So how the tension force will act on the pulley near here and near here, towards the right or towards the left? Tell me. What tension will
Towards
do to
right.
the pulley? It will pull only, right? So at this point, it is going to pull like this. Yes or no? Tell me, Rugved. The force of tension on the pulley near that end will be towards right. Yes or no?
Yes, sir.
Do you realize this?
Yes.
And you can also see something. The pulley is fixed. So the tension acting on the pulley is towards right. So can you think about who is balancing the force to stop the pulley? Because technically the pulley should go right, but it is not going. Can you explain why? Why it is not going towards right? Because it's I'm saying it's a fixed pulley. So fixed means it will have some axle over which it turns. So axle is kind of fixed. So who must be balancing the tension force on the pulley?
Axle.
Exactly. It is the force by the axle on the pulley, right? And
Yes.
how much force will be applied by the axle on the pulley? On the left?
2T.
Exactly. Siddhant, do you realize this?
Yes, sir.
So 2T is the force on pulley by axle. So you will be asked these kind of questions. Okay. So just two more situations, then I will leave you maybe early only. So theoretically, if you are done with this concept, then we can solve, start solving question from the next lecture. If you have a pulley and let's say the pulley is kind of fixed. No, not fixed. Let's say it is attached to. It is attached to some string near the axle. I'm not showing the entire diagram. And there is a rope passing over the pulley. So if the pulley is smooth, and light or massless, all the other terms they use massless. Can we say the tension here and here will be same? Let's call the tension as T and T here. And the tension here will be, let's call T dash. Okay. Now think pulley as an object. The mass of the pulley is 0. So T dash will pull or push the center of the pulley. What it will do? T dash will pull the center or push the center.
Pull.
Tension only pulls. It will act like this way. Correct? And the other two tension will pull like this. Okay. Now, it is quite possible that the pulley may be accelerating right or left. I don't know. What is Newton's laws of motion second law? From Newton's second law, we derive it for constant mass. For constant mass, the F external is equals to F net, and F net equals to mass into acceleration. Luckily, we know this answer. So here we can write as, let's say the pulley is accelerating towards the right with an acceleration A. So who will accelerate it? 2t or t dash? Who will support the acceleration? If the pulley is accelerating towards right, then who will support the motion? T or t dash?
T.
So 2t is acting towards right and t dash is acting left. So the net force we can write as 2t minus t dash. Am I right?
Yes.
As per the Newton's second law, for constant mass, net force we can write as mass into acceleration. But we know that mass is tending to 0 because pulley is massless. And that will lead to the fact that 2t minus t dash is 0. Therefore, t dash is nothing but 2t. Now, this unique answer is only for the massless pulley. So a massless pulley will make sure that if you know the tension on the one side, you can write the tension on the other side with ease. And also, you need to realize one more thing. A massless pulley can accelerate with 0 net force. Yeah, that's correct. Because here this term is 0 because of M, not because of A. So A may be non-zero. So for massless pulley, whether it is accelerating or not, force on two opposite sides must be balanced. All are coming because of the assumption which we have made. Okay. So in the laws of motion chapter, our pulley will be always smooth by default. If you read the literature or the question statement, you will come to know it is always smooth. Okay, so now you prepare for your examination. We'll continue the next lecture. Till then, okay, next lecture is on Friday. Yeah.
Yes, sir.
Okay, so you can you keep the Friday lecture? No, that's fine. Let's keep in the evening only. All right. So Friday will be lecture on the evening because I think Saturday, Sunday is 31st, right? So you will have holiday now. Okay, so to be continued.